Given a positive integer n, find the least number of perfect square numbers which sum up to n. If you have a number n that is 12, the least number of square numbers will be 3 because it can be made up of 3 perfect squares, which is 4, because 4 is 2's square. If you try to make 12 from 9, then 12 minus 9 will be 3, then 3 will take 3 perfect squares, which is 1, right? 3 needs to take 3 ones. So 12, if you choose 9, it will take 4 instead of 3. So 3 will beat 4. And similarly, if n is 13, it will take 2. Pause the video and see if you can solve it. We know that any number that is not a perfect square need to be composed by a number that is smaller. For a number that is perfect square, obviously it will be 1, right? For example, 1 is just 1, 4 is just 1, 9 is just 1, because they are perfect squares themselves. If a number is not a perfect square, for example 12, it needs to be composed by a smaller component. So we have a couple of options, right? So 12, should I choose 1 square, or should I choose 2 square, or should I choose 3 square? And we know we need to stop at 3 because we need to choose until the floor of the square root of that number, right? Square root of 12 is 3 point something. If you floor it, it will be 3. So what happens if you choose 1? 12 minus 1 gives you 11. And now we need to find out what is the least number of perfect squares which sum up to 11. Before we go into further details, let us pause for a second and think of what is the intuition for this problem. You are given a number 12, and you need to make some choices, and after each choice, the number becomes smaller and smaller, right? Because at 11, you also need to make some choice, maybe 1 square or 2 square or 3 square. After each choice, the number becomes smaller until it boils down to a base case. And the base case is not necessarily 1. The base case is just a perfect square, meaning if you hit a number that is a perfect square, you can return 1 straight away. If you choose the path at the middle, 12 go into 2 square, you will be left with 8. And 8 is not a perfect square, so you need to keep going, right? And 8, you can only go 1 square or 2 square. And suppose you take the path on the right, you take 2 squares, so you are left with 4. And 4 is the base case because it is a perfect square. It is 2 square. So how many perfect squares does it take in this path? It is 3, right? So 1 plus 1 plus 1. It is 3 perfect numbers. Just to avoid confusion, I'm drawing this diagram not according to actual code sequence. Because we are doing DFS, the actual code sequence is going to look something like this. If you hit a base case, you will return, and go into other case, then you return, then you come here, hit a base case, you return. So this is what it looks like in DFS, right? But this layout looks more BFS. I'm only laying out this way to help with visualization, not according to actual code sequence. Okay, so assuming we are right here, we are 11 and choose the path of 1 square, so you are left with 10. Okay, so what if you are at this path? 11 minus 4 will be 7. Okay, so what if you are here? 11 minus 9 becomes 2. What about 8? You can only choose 1 square or 2 square. So 8, if you choose 1 square, it will become 7. And you notice something, we have a duplication of calculation. Because we are doing DFS, this path will definitely be executed first. So the least number of perfect squares which sum up to 7 should already be known at the point we reach this path. And if we just calculate by ourselves, 7 should take 4 perfect squares, right? Because 7 is 2 square plus 1 square plus 1 square plus 1 square. We already know the result for 7. So when we are here, when we are 12, go to 8, go to 7, we no longer need to do the calculation. we can return the result of 4 straight away. So this is called dynamic programming, right? If you don't know what dynamic programming is, it just means caching. Cache the intermediate results. So the next time you see it, you don't have to calculate it again because you already saved it somewhere. And in this question, you can save it in an array of size 13. So you have 0 all the way to 12. We have our array here. This row is the row of the number, and the next row is the result of the least number of perfect squares to sum it up. And at 7, we can cache the result 4. So we can input 4 after here, right? Then the next time we see it, we can retrieve the result from this DP array. If you are interested, you can walk through the entire call chain on your own. So now I'm going to code it up. First, we need a DP array. And our DP array will have the size of n plus 1. Let me just have a helper function called the minimum number of squares to make up a input number, n. And first, we take a look at the cache. The cache is DP. And it's important to label whether a number has been cached. So I'm going to put the label as -1. As long as the number is greater than -1, we know that the result has been written into cache. Else, you have to calculate it. Then we need to make some choices. And among all these choices, there are good choices, there are bad choices. So we can initialize the choice as n. And at the end, we will write the result to the cache. And how do we make choices? The choice is what square to choose. It should start from I, and the number square should not exceed the number itself. The fact that we make a choice of using I square means we have used one perfect number. So the number of perfect numbers will be 1 plus the number left. The number left will be n minus I squared. So this is the number of perfect squares for this choice. And we will select the best choice by choosing the minimum between the result and our current choice. See if it works. And submit. Now this works, but it's not very efficient. It's not efficient is because we are exploring every possible choice. At every node, we are exploring all the possible choices. At 12, you're exploring 1 square, 2 square, 3 square. You can imagine if the node number is very big, you will explore a lot of choices. And although you are using DP, your caching result is still very slow. In order to improve the performance, we can think of greedy. Greedy means you are not exploring all the choices, you are picking. You are being greedy. What should we be greedy about? We should be greedy about the number of perfect squares that we allow. If you want to be the greediest, you will only allow 1 perfect square. So that's when you are as greedy as possible. You're essentially saying, hey, 12, you must be a perfect square. And of course, we know 12 is not a perfect square, so this assumption is wrong. But that's fine, because the whole point of greedy is to be as greedy as possible and test whether it actually works. If it doesn't, you will loosen the criteria. You loosen the criteria by allowing more perfect squares. and allowing more perfect squares, all the way until the number itself. And the reason we will allow until the number itself is because for numbers that are either 1 or 2 or 3, it will take the number itself number of perfect squares, right? Because 1 is 1 square, 2 it needs 1 plus 1, 3 needs 1 plus 1 plus 1. So in the worst case, you will need the number itself number of perfect squares. But as long as the number is 4 and greater, you will know the number of perfect squares is definitely less than the number itself. So this number 12 will never be hit in reality. Just now we were being too greedy. We only allow 1 perfect square and it doesn't work. So now let's try 2. Can 12 be made up of 2 perfect squares? And how do we answer that question? We can only break down a question into an easier question. So we break it down by making a choice. 12 can be made up of 1 square, 2 square, or 3 square. If you choose 1 square, 12 will become 11. If you choose 2 square, 12 become 8. 3 square, 12 become 3. And because by making this choice, you have exhausted 1 perfect square, so the perfect squares left is 1. And you need to ask, is 11 a perfect square? Nah. Is 8 perfect square? Nah. 3? Nah. So you know that this path of asking can 12 be made out of 2 perfect squares doesn't work. So you know that I'm being too greedy. Let me relax the rules by asking the question of can 12 be made out of 3 perfect squares? And how do you answer that question? We also need to make a choice. 12, 1 square, 2 square, 3 square. Then here you have 11, 8, and 3. This is all the same. But instead of 1 here, you have 2 here. Right? By making a choice of which perfect number that I want to make up myself, I exhausted count of 1. So from 3, I exhaust count of 1 to 2. So I'm asking the question, hey, 11, can you be made out of 2 perfect squares? Then 11 say, okay, let me break down the question into easier one. 1 square, 2 square, 3 square. Here will be 10, 7, and 2. And this will be 1. So you are asking the question, hey, are these perfect squares? No, none of them are. So you know that 11 failed. Okay, then we look at 8. 8, can you be made out of 2 perfect squares? So 8 want to break down the question into easier one. 1 square, 2 square. Here we'll have 7 and 4. 1, 1. So 7 is not a perfect square, but hey, 4 is a perfect square. The significance of this is we know that 8 can be made out of 2 perfect squares, and we know that 12 can be made out of 3 perfect squares. Now, because we are being greedy, do you need to explore all the other possibilities? No, right? Because we want to find the least number of perfect squares, and because we are being greedy, we go from as greedy as possible to more relaxed rules. So all the other parts of the tree you don't need to traverse anymore. And that's the intuition behind why greedy is faster than dynamic programming, because you're being greedy. You don't need to traverse every part of the tree, whereas in dynamic programming, you do explore every part of the tree despite caching. So let's code it up. We're going to have a helper function called can divide by count. So we have a number n, whether it can be divided by count. And because we want to be greedy, the count will go from 1 to n. And if can divide by count is true, n and I, we will return count. This return should never be hit. If you are at count of 1, you're essentially asking, are you a perfect square? So let's test whether you are a perfect square. Square root is square root. If the count is not 1, we need to break down the question into smaller pieces. So you make a choice of a perfect number, I square, and can you divide by, the number will be n minus I square, and the count will be count minus 1. If this is true, you return true, else return false. See if it works. Okay, so this is count. So there we go. And you can tell that if you use greedy, it's much faster than dynamic programming.